Welcome to this course on Introduction to Electrochemical Engineering. My name is Raj Pala and I'm in the Department of Chemical Engineering. I'm also an associate faculty of the Material Science program in Indian Institute of Technology at Kanpur. So this is an introductory lecture. Engineering students often want a context when asked to learn about a particular subject. With respect to electrochemical engineering, there's a lot of activity around batteries, how to utilize batteries for electric vehicles. As engineers, we would like to understand the fundamental working principle behind batteries and optimally design these batteries. While there is a lot of activity in this area, the subject matter of electrochemical science and engineering is not something very recent. It has been around for a long time. For example, if you look at the time scales mentioned here, it is around 1807. Okay, so this was the time where the applied chemist Humphrey Davy tried to extract very hard to extract metals, metals that cannot be extracted otherwise by other means. So he tried to extract it by electrochemical means. Usually these are alkali metals and so on, like lithium, sodium, potassium. And a big success with respect to electrochemical refining or electrochemical extraction of metals occurred with this process, with the extraction of aluminum. Again, it's important to look at the time scales involved in the development of new technologies. While it's not so productive to teach philosophy of a particular subject matter, it's productive to have a good understanding of history of the subject matter. So I would emphasize certain historical aspects as we move along in this course. So if you look at the development of electrochemistry, Michael Faraday played an important role, and Michael Faraday was a technical assistant of Humphrey Davy. In those times, this organization structure of PhD advisor and student was not well established, but typically someone went and worked with practicing chemists and in this case, practicing chemists, and then learned the field and made advancement. So Michael Faraday went and worked with Humphrey Davy, and he came up with Faraday's laws of electrolysis in around 1834. He showed the importance of utilizing electrons to do a lot of chemistry. Okay, so what is the advantage over thermal means? Before that, most of the reactions were done thermally. From the time of Humphrey Davy, there was a systematic approach towards undertaking reactions via electrons. And Michael Faraday played a big role in establishing certain fundamental and elementary laws of electrolysis. After this, Michael Faraday went and worked in electricity and magnetism, wherein he made many contributions. Even though batteries are of wide utilization nowadays, there has been the promise of fuel cell. In many respects, the working of a fuel cell is very much similar to that of batteries. We would hear a theme in the course, I will emphasize often, that the electrochemical devices, energy producing electrochemical devices are not limited by Carnot efficiency. So if you look at a heat engine, wherein you are using a chemical fuel to generate work, they are often limited by Carnot efficiency. Okay, so that's a big limitation. Whereas in an electrochemical device like a battery or a fuel cell, the chemical fuel is utilized to generate electrical power, electrical work. That is not limited by Carnot efficiency. So that has been the promise of fuel cells and batteries, that you can better utilize the energy generated by oxidation or combustion of a fuel. Again, fuel cell is not a recent topic. The first fuel cell was demonstrated by the scientist group in 1838. So despite this demonstration, fuel cells are not so prevalent as a battery. We will see why. What are the technological challenges that has been limiting the widespread utilization of fuel cell. That's one of the aspects we will look into in this course. Not everything needs to be hot. There are many things that are very fundamental. Electrochemistry plays extremely important role in biology. In fact, every sensor in human body has an electrochemical working principle. For example, how does the tongue sense taste? This is one of the areas we work in. We undertake research in our lab in this area. How does the nose sense smell? All these things are electrochemical devices. So all the sensing is done via electrochemistry, and the entire brain is an electrochemical device. The signal transduction in human body is accomplished by nerves, and electrochemistry plays a central role in both sensing and signal transduction in biology. So again, if you look at the time scales, Louis Galvani demonstrated the certain fundamental observations between applying potential and movement in biological system. Although Galvani demonstrated these observations, it was better interpreted by Volta, and he called this device as the device he demonstrated as an artificial electric organ. So again, this happened in 1800. Okay, so this is not something recent. So a lot has happened in terms of understanding and widespread utility from this time to when we live now. So while all these things like batteries and fuel cell look maybe more glamorous, and these biological applications look very fundamental, there are other mundane but very important applications. For example, corrosion and corrosion prevention are very fundamental electrochemical processes in operation. You would see if you want to suppress corrosion, okay, which plays a huge role, debilitating role in our environment, you have to utilize the principles of electrochemistry to suppress corrosion. So if you look around, I would challenge for you to identify at least 10 devices within your household where you live, where electrochemistry plays a big role. Okay, so the goal of this course would be to understand how these electrochemical devices work from very fundamental principles, using principles of thermodynamics transport and electrochemical kinetics, and how do you use these principles to design these electrochemical devices. So how would we care about these devices? We would analyze and synthesize. What exactly do I mean by that? By analysis, what I am referring to is utilizing the principles of thermodynamics, electrochemical kinetics, and electrochemical transport phenomena principles to understand how an electrochemical device, it can be a natural device like what is observed in a human body, or an engineered device like a battery. We're going to use these principles to analyze such devices. Often, this is a course in electrochemical engineering. So the procedure we will utilize will often involve macroscopic principles. However, we will also utilize certain molecular principles to unfold principles of electrochemical systems, and we will often make connections with electrochemical measurements. Okay, so if right from the early days of electrochemical science, measurements played a very important role in electrochemistry. So in fact, these measurements are not very easy to understand. There is a lot of non-triviality associated with electrochemical measurement techniques. So we will emphasize the subtleties subtleties behind electrochemical measurements. So what we mean by synthesis is product and process design in electrochemical engineering. A battery is an electrochemical product. What do I mean by that? It's not just a it's just not an aspect of chemistry. So there are chemistry plays an important role in the design of batteries, but there are a lot of other principles, especially principles of kinetics and transport phenomena, that come into play when you design this electrochemical product. So we'll emphasize such principles in this course. And it is not just about electrochemical products. There are a lot of important electrochemicals that are that play a big role. These are commodity chemicals, especially in the area of chloralkali industries, where electrochemistry plays a central role. So there are a lot of electrochemical process design. We'll also touch upon such principles in this course. So the emphasis will be on product and process design in the context of energy and chemical transformation. Although electrochemistry plays a big role in biology, we will not be able to elaborate on this aspect a lot, but we will talk about certain electrochemical sensors and electrochemical signal transduction in biology as we go along in this course. So what does a simple electrochemical cell comprise of? It comprises of two material systems. One is an electronic conductor and another is an ionic conductor. In fact, a lot of action occurs at the interface between the electronic conductor and an ionic conductor. What we show here is a Daniell cell. It contains a zinc electrode, that is one of the electronic conductor here, and another electrode is copper. Again, that's an electronic conductor. So there is a small ambiguity in the word electrode. Most of the time we would be referring to the electronic conductor as the electrode. However, because interfaces play such an important role in electrochemistry, when we talk about the electronic conductor, we cannot really isolate what is happening at the interface. So often when you refer to electrode or electrodics, we're not only talking about the electronic conductor, but we are also talking about the interfacial processes and the interfacial region associated with the electrode. So this is an energy generating device. This Daniel cell is an energy generating device. So what is the fuel here? The fuel here is actually zinc effectively getting oxidized to zinc 2 plus and copper 2 plus getting reduced to copper. Okay, so this is the actual fuel, that is the zinc oxidation to zinc 2 plus and copper 2 plus reduction to copper. So this chemical change, if you write the chemical change is zinc getting oxidized and copper getting reduced, okay, the overall reaction might not look as if it involves electrons, okay. But if you decompose this, break down this reaction into oxidation and reduction, you would see the importance of electrons. While zinc gets oxidized and copper 2 plus gets reduced, you generate electrical power, electrical potential that can be measured by a voltmeter. We'll go into these measurements later in this course. This is just an introductory lecture. And such a potential can be, a potential that is generated can be utilized for passing current via a load. Okay, so this can be a simple electrical bulb or can be more power intensive device. While these wires conduct electronic current, what is conducted in the ionic conductor are currents generated due to transport of ions. Okay, so in this case, the relevant ions are zinc 2 plus and copper 2 plus, and there are sulfate ions. Okay, so often in an electrochemical cell, there is a separator. It may play many roles. We will elaborate the role of a separator as we go along. But the simplest role it plays is it separates two compartments, the anode compartment as well as the cathode compartment. Again, we'll clarify what you mean by anode and the cathode. So at the anode, there is oxidation. At the cathode, there is reduction. So there is always anodic oxidation, cathodic reduction. And there is a compartment. There is an electrolyte that is in contact with the cathode in this case, and there's an electrolyte that is in contact with the anode. What the electrolyte, again, there's an ambiguity in the terminology. Electrolyte might refer to the salt that is dissolved in a solution. In this case, it's an aqueous solution. Put together, we may call that as an electrolyte. Sometimes you may often just refer to the salt as the electrolyte. Okay, so depending on the context, the way we use this term will become clear. So thing to notice is that there is a continuity in current. While electronic current is conducted via the wire, there is also an ionic current, the effective current transport. Okay, so this is like something what we see in basic electrical circuits. Okay, so a lot of theorems which is are a consequence of charge conservation. The net current that is going around in a circuit has to be zero. If not, there will be charge accumulation. To prevent charge accumulation, you have a condition. There is a continuity in current transport. The electronic current that is conducted via the wire is equal to the ionic current that is conducted. So just to emphasize, the simple electrochemical cell has the following components. It consists of electrode and ionic conductor. This is often called an electrolyte, and the action is at the interface between electrode and the electrolyte. What is so special about electrochemical cells as opposed to a chemical cell? Electrons play the central role in electrochemical device. Okay, so in some ways, the main actors are actually electrons. Okay, so if you want to do, let's say, an endothermic process. Okay, so one approach, or the approach that was utilized before electrochemical process, was a thermal process. Okay, so what you typically do is you heat the system, and the heat provided, for example, to the reactants, goes towards increasing the temperature. What do you mean by that? By equipartition theorem, temperature can be represented, can be thought of as the average kinetic energy stored in different degrees of freedom. All right. So typically, when you heat the system, you are increasing the thermal energy available in different degrees of freedom. So this thermal energy is utilized for overcoming the activation barrier that is often involved in endothermic reaction. So as opposed to this, there is a different way of providing this activation energy. So electrochemical approaches employ an electrochemical potential and increase the energy of the electron, and such an electrochemical activation plays an important role in electrochemical devices. So this is a very qualitative description. We will make it much more physical, physicochemical, and quantitative as we progress in this course. But the point to be emphasized is that electrons play an important role in electrochemical devices, and electrical activation has enormous consequence and effectiveness as opposed to thermal activation. So in the earliest slide, I emphasized this Carnot limitation. That is, the electrochemical devices are not limited by Carnot efficiency. We will see why. Okay, so that is closely associated with electrochemical activation. Okay, so electrochemical energy transfer. Okay, so these are these are jargons for now, but we'll clarify these terms as we progress in this course. Okay, so right now I want to just make the distinction that the normal chemical reactions are thermal reactions, but electrochemical reactions involve activation of electrons. Okay, so even if you have a battery, in a battery, there is an exothermic reaction that is taking place. This energy release because of the exothermic reaction gives you electrical power. Again, even in this case, electrons play a important role, okay, significant role. In fact, the potential difference that you will develop that is generated in a battery will be interpreted in terms of the energy of the electrons between these two electrodes. So in this electrode, the energy of the electron is different from the energy of electrons in this electrode, and the difference between these two energy levels is what a voltmeter will measure. Again, this will be emphasized. These are all very important and subtle points. We'll be touching upon these aspects as we progress in this course. So electrochemical cells can be broadly classified as being a galvanic cell and an electrolytic cell. A galvanic cell is an energy generating device. A battery, fuel cell, these are all galvanic cell. Okay. So here we are schematically showing the most common battery, which you might have seen before lithium-ion battery, you might have seen lead-acid battery. Okay, so every car, at least the older cars, have a lead-acid battery, and also the UPS, uninterrupted power supply, which you have at your home, often has just a lead-acid battery and not a lithium-ion battery. Lithium-ion battery are more common in your laptop, as well as phone. We will see why that is so. But for a stationary battery, lead-acid battery are more common. So again, lead and lead oxide, okay, lead dioxide, these are electronic conductors in a lead-acid battery, and these are the electrolytes. And there are some chemical reactions, we won't go into the detail, that occur at the interface between the electrodes and electrolyte. So the same lead-acid battery can operate both in the galvanic mode as well as an electrolytic cell. In the galvanic mode, the fuel is utilized to generate an electrical power. And in electrolytic cell, the opposite happens. Okay, so that is, you are imposing an external power to reverse the flow of the battery. Okay, so the discharge of the battery is called the galvanic operation of the lead-acid battery. Okay, so there's one way to differentiate the galvanic and the electrolytic operation. From thermodynamics, we can calculate what is the equilibrium cell potential. In the case of a lead-acid battery, the equilibrium cell potential is about 2 volts. So in a galvanic operation of this system, the battery is being discharged. Okay, so during the discharge of the battery, the potential which you obtain is less than the maximum potential that is theoretically obtainable. Okay, so theoretically obtainable potential, which can be calculated from thermodynamic principles of thermodynamics, let's say it's about 2. We never get 2, we get something less than 2. Okay, so the difference between the potential which you get from the battery and the equilibrium potential is called polarization. Okay, so the polarization can also be defined in the electrolytic operation. So in this region, the system operates as a galvanic cell. So the fuel is being consumed and a potential is being generated. The charging of a battery, okay, so when the battery is completely discharged, all the processes can be more or less reversed. Okay, so I emphasize just more or less because there's a finite cycle life, okay, to a battery. How many times the battery can be charged and discharged. Okay, so ideally we would want it to be infinite times, but that's not often possible. A good battery can be charged probably, let's say 2,000 times. A very good battery can be charged, discharged, let's say about 5,000 times. Okay, so when you charge a battery, you're operating the electrochemical cell as an electrolytic cell. Okay, so here the voltage that is being imposed is more than the equilibrium potential. As you can see, you're imposing about 2.2 volts, and such voltage imposition reverses all the electrochemical processes. Okay, so we will see what are these electrochemical processes we are referring to in much greater detail as we progress in this course. So for now, 2 things have to be emphasized. There are 2 ways you can operate an electrochemical cell: an energy generating process. In this case, you're generating electrical work. Okay, so I mean, probably the right terminology is electrical work generation. Okay, that's called the galvanic operation. Sometimes you are just imposing an external potential and generating certain chemicals. That's called electrolytic cell. Both play a very important role. Batteries and fuel cell are in this. These are galvanic systems, but let's say chloralkali cells. Okay, so we'll see a lot of electrochemicals are generated, and these are all electrolytic operations of an electrochemical cell. Water electrolysis is probably the most common electrolytic cell, which you might have seen, probably done some experiments in your high school. So in water electrolysis, in impose an external voltage, the equilibrium voltage is 1.23. When you impose, let's say, an external voltage of 1.6, say, you are generating hydrogen and oxygen at 2 electrodes. Okay, water is split into hydrogen and oxygen. This is one of the purest way of generating. If you want to generate the very pure hydrogen and very pure oxygen, you employ electrolysis. Again, this is a large, it is utilized. Water electrolysis is done extensively in the industry due to certain technical reasons. We will go into these reasons later in this course. Where do we go from here? In the next lecture, we will look at fairly elementary electrochemical principles. These are what you've been taught in your high school probably, involving flow of currents and certain Ohm's law and so on, and how Michael Faraday introduced certain laws. I mean, these laws are actually just bookkeeping principles. Okay, so Faraday's laws of electrolysis is mostly bookkeeping principles, but even though they are fairly elementary, it's important you have a good grasp of such principles. That's what we will cover in the next lecture. Thank you.